All right, here we are in chapter 10, correlation and regression. So now we're in the red portion of the flow chart that I've been using. When we want to ask questions about the relationship between two continuous variables, or we want to see if one variable predicts another variable, we use correlations for relationships and regression for prediction. So a correlation is a statistical technique that we use to measure and describe linear relationships between two variables. The variables are not manipulated, and it requires two scores for each individual. So you need to have, if we're looking at people, we would need to have one subject and two measures on a continuous scale for that individual. You're going to list it in a table or as a scatter plot. It's sometimes referred to as the Pearson product moment correlation coefficient, and it's denoted by the lowercase r. There are other correlation coefficients for nonlinear or other types of relationships, but we're only going to cover the linear one here. There's Spearman's rho and point biserial and all these other types of correlation coefficients, but we're just going to cover this one. So in order to do it, you need to have, like I said, two measures, an x and a y, paired for one individual, and they come from a simple random sample of quantitative data. You need to visually examine the scatter plot before you get started to see that you have somewhat of a linear relationship and make sure that you're using the right correlation coefficient. In the book, there's a note about bivariate normality. So at a fixed value of x, the y need to be normally distributed and vice versa. We're just going to assume normality for a sufficiently large sample, so greater than 30. Outliers do radically affect the results, so you want to make sure that if you do have outliers, that they're not data errors that need to be corrected. Okay, so the characteristics of correlation is, the first is the strength. So the strength of the relationship has to do with the magnitude, not the sign of the correlation coefficient. So a correlation coefficient of negative 0.87 is stronger than 0.80 because 87 is bigger than 80, right? 0.87 is larger than 0.80. It doesn't matter about the sign. Scale. If all the values of either variable are converted to a different scale, it doesn't change the correlation. They're also interchangeable. It doesn't matter who's x or who is y. It doesn't change the relationship. And then the sign denotes direction, not magnitude. And we're talking about the linear correlation. All right, so here we have a positive when it goes up and to the right. We have a positive correlation when it goes down and to the right. We have a negative correlation. This one's a stronger correlation than this one. So negative 0.97 is a stronger relationship than 0.89, and it's because these are more tightly close around a fit line. Here we have a blob of no trend, pretty much, and so that's almost a 0. So we say that's no correlation. And here we have a correlation of 0.33, which is not bad. It's a decent correlation. However, you can see a clear linear, curvilinear trend to these data. And so sure, you can put a fit line through here, but you're going to miss a lot of your data. So cautions. Correlation always does not imply causation. Just because they're related does not mean one cause the other. You need to have a true experiment in order to determine causation. Your values can be, the value of your correlation can be affected by the range of scores. It can be affected by outliers, and we should not interpret these correlations as proportions. So let's do an example. On page 448. Is there a relationship between pulse rate and white blood cell count? Now we have a tiny little data set. We have 5 subjects, and we have their pulse rate and their white blood cell count. I drop these into SPSS. I don't need to do any kind of value labels. They're just quantitative, numeric data. Name them both. And then the first thing I want to do is, do we have a linear relationship? Am I using the right correlation coefficient? So we can do this in many different ways, but the easiest is to go to Graphs, Legacy Dialogues, come down and go to Scatter Dot. You'll click Simple Scatter. It'll put this box around the picture here, and we'll select that one. We'll bring pulse rate over and white blood cell count over. It doesn't matter which one's X and which one's Y. We'll click OK, and we get this little bitty scatter plot. Okay, hard to tell what's going on. Mentally, I try to draw a fit line, right? This data point could be pulling it more this way. I'm going to cheat and use the computer. So the computer drew the fit line for me. You can see it hugs most of there's more of these data points up here, and so this one is the outlier. So let's go through the steps. We're going to state the null and the alternate hypothesis. Is there a significant relationship between pulse rate and white blood cell count? There is no relationship between pulse rate and white blood cell count. The alternate is that there is a relationship between pulse rate and white blood cell count. Before we were using the Greek letters. This is P, looks like a P, but it's not. It's the Greek lowercase r, which is pronounced rho. We're not going to use these anymore. I just want you to use the words. A note about degrees of freedom. When you have two data points, you can draw a line between them, right? And they both line up on that line. So that would be a perfect correlation. All right, so in a sample of only two data points, that's perfect correlation. So in order to have degrees of freedom for the sample correlation, it's free to vary only when the data set has more than 2 points. So the degrees of freedom is sample size minus 2. Oops. Okay. So how do I do it? I go to Analyze, I come down to Correlate, I go to Bivariate, and I bring these over. Now I can click on this one and drag and drop it up here. I can change the order that way. It's very easy. We just leave everything like it is, and we click OK. And we get our output. So we had the hypothesis on the other slide. The alpha level is 0.05. We did SPSS, did the test statistic for us, and we're going to state our conclusion. So remember that for correlation, the degrees of freedom is n minus 2. We get the sample size here is 5. So our degrees of freedom goes here. It's n minus 2, so 5 minus 2 is 3. So we say results indicate that there's no statistically significant relationship between pulse rates and white blood cell counts, and we'd write it out. Now look here, I have a red box here and a red box here, and inside those two boxes is exactly the same information. I have the correlation coefficient up here, I have my significance here, not significant, and I have it here. Well, when we're doing correlation, it's a matrix, and so we have a mirror image up here in the upper right hand corner and the lower left hand corner. When we have pulse rate correlated with pulse rate, it's going to make a perfect correlation. When we have white blood cell count and white blood cell count correlated with itself, it's going to be a perfect correlation. So around the ones, you're just going to report one side or the bottom side. You don't have to do the entire matrix. Now here we only did one correlation, so you could just write it out. But if you had multiple correlation coefficients that you were calculating at the same time, you would want to present that in a table that would look like this. And this is a shameless plug, I see, but this is a paper that I published with a colleague about science and social studies assessments. And you can see that I have this little triangle of data up here. I don't need it down here. It just gets busy on the eyes. We don't need to do redundant information. So I picked the upper right-hand corner. Some people pick the lower left-hand corner. It's just personal taste. I did science assessments, social studies assessments. This is an APA table. In the homework, I'm going to give you one that you will fill in. So that's what that looks like. So before we walk away from correlation, we do have an effect size for correlation. If I just square that correlation coefficient, I get this thing called coefficient of determination. It's a different type of effect size. Since correlation can't be interpreted as a proportion, we can square it and get this coefficient, which can be treated as a percentage. So it measures the proportion of the variability in one variable that can be determined from the relationship of the other, which is just like the eta and the partial eta squared from ANOVA. So we just square it, and we'd report it out just like this, right? R of 3 degrees of freedom is 0.405. Now it wasn't significant, but still for instructional purposes, I'm going to do the coefficient of determination. So when you square things, you multiply it by itself, and I get 0.164. And so that's 16.4%. So 16.4% of the variation of the pulse rates is accounted for by white blood cell counts. Okay, so then the final write-up, like I just said, if you wouldn't calculate the R-square if you don't have significant correlations, but I'm going to show you how to do the whole thing as though we did. So results indicate that there is no statistically significant relationship between pulse rates and white blood cell counts. Write it out and present the coefficient of determination like that. Then I would say, therefore, 16.4% of the variation in pulse rates is accounted for by white blood cell counts. Okay, simple linear regression. It's called simple because there is only one independent variable. Now, I'm not going to lie, regression is kind of complicated. It's very similar to ANOVA, but there's a little bit more going on. And I took a full 2 long semesters on regression in my graduate program. So it's a tall order to teach you everything I know in one PowerPoint. So I'm just going to cover simple linear regression. I'm going to touch on multiple and logistic, and then I give you supplemental information if you need that information for your project or you just want to have it for reference. But I'm only going to just touch on it here. I'm going to go into depth on simple linear regression, and that's it. So linear regression is a statistical technique for finding the best fitting straight line for a set of data. You have an independent variable and a dependent variable. There's different vocabulary words, right? So we have independent variables also called the predictor or the explanatory variable, and the dependent variable is the criterion or the outcome variable. The linear relationship can be explained by this equation. Remember in middle school we had y equals mx plus b? Well, this is the same thing, mx plus b, but in regression terms, we're going to talk about it in terms of y hat. These are the predicted y's, the predicted outcome variable, and this is a beta. Beta naught is the intercept, and beta 1, x, beta 1 is the slope, and x is our explanatory variable, or our predictor. Okay, we'll talk more about that, and it'll become clearer. So if some types of things I can do with regression, I can make predictions. So if I know someone's height, can I predict their weight? We also can say that we regress weight on height. So we regress the y variable on the x variable. You might see that. Another question would be, if I know your score on test 1, can I predict your score on test 2? So the only difference between correlation and regression is that we start correlation with looking at the scatter plot and the distance around the scatter, right? Remember the scatter around the y axis and the scatter around the x axis from the video that you watched, the YouTube video. Now we're drawing the fit line. And the best fit line, here it is, it's the same equation. The distance between the predicted values and the actual measured values from the sample is called the residual. It's also known as error. Okay, so how well a set of data points fit a straight line can be measured by calculating the distance between those data points and the line. We use that formula to find the predicted value of y. This is called y hat, and it's hard to make that little doodad, so I'm just going to, sometimes I might just say y hat instead of making that little symbol. And the error distance is called the residual. It's just like I showed you, the distance between the predicted y and the actual y. Because some distances may be negative, each distance should be squared so that all measures are positive, and this is why it's called ordinary least squares. So it works the same way as correlation. You need 2 scores for every individual. You have one score's predictor now, and one's the predicted or criterion. Now it matters who's x and who is y, and like I said, we regress y on x. So there's 2 parts of a regression. You have the predicted variability over the unpredicted variability. And this is a little bit more information than you really need because we're not going to be calculating these by hand. But the vocabulary is very much the same as what's in ANOVA. All right, so when we have, like I say here, I'm going to spare you the details, but the output of regression equation is very much the same as that of ANOVA. The only difference is the x variable. And in ANOVA, the x variable, the independent variable, is categorical. So we want to know, is there a difference in scores between UTMB online classes versus face-to-face classes? The outcome variable would be the score. The independent variable would be group, online versus face-to-face. And in regression, the x variable is continuous. So for example, score on quiz 1, does it predict score on quiz 2? But in reality, you can also have categorical variables in regression, but you'd need to dummy code them, and I'm going to talk briefly about that at the end of the PowerPoint. But this is not necessarily set in stone. So regression can have a categorical IV as well. All right, and so the only difference here, we have the F statistic, we have the numerator and the denominator for our degrees of freedom. And here, before, we talked about the mean square between and the mean square within. Now we're just talking about the mean square regression and the mean square residual, but it's the same calculation. So, research question 1. Does percent body fat predict body mass index? I'm going to use this data set that I have, and we're going to say our null and alternate hypothesis. Percent body fat does not predict BMI, and the alternate is percent body fat does predict BMI. Our alpha is always 0.05, and we're going to calculate the test statistic. So we're using the body fat data set. We always have to deal with our assumptions. The first one is that the residuals now are normally distributed, that we have no influential points. These are those outliers that greatly affect the regression. We're going to look at Cook's D, which stands for distance, and we want values not to be greater than 1. So these are influential points which can screw up our regression. So we want everything to be less than 1. And then we want to look at our residual plot, the graph of the y and the x minus y, and the y minus y hat values that show no pattern in the data. We just want this big blob of data points within plus or minus 3 standard deviations along the x and y axes. I'll show you that as well. So, like we do with correlation, we want to see, let's just take a look at our scatter plot, and we can see we have kind of a nice positive trend. We have a few outliers here, which may or may not be a problem. I ran a quick correlation. I see 0.726, and I get these little stars, right? SPSS will flag significant correlations. This one's at the 0.01 level. If it had 1 star, it'd be at the 0.05 level. And you can see the significance here. And our sample size is much larger in this data set. We have 252 observations, so our degrees of freedom would be 250. All right, so we go to Analyze, Regression, Linear. I bring my dependent variable over, BMI, and I bring my independent variable over, body fat, percent body fat. Then I click Statistics. And here I am. I click Estimates. I can click Confidence Intervals, Model Fit, and Descriptives. Model Fit, I think, is already checked. I just had to click this one, and this one. Then I click Plots. Now, we're going to move the Z predicted, which is the y hat value, to the x-axis, and the Z residual to the y-axis. And I always remember this kind of crisscross pattern, which is why I did it like this. So I do the Z predicted goes in the x, and Z resid goes in the y. Then I click this normal probability plot. Then I click Save and click OK. Now the first thing the only thing here is you need to check is this Cook's distance, right? And then we click Continue, and this is just a repeat of what I've said before. We want to make sure that our standardized residuals are not bigger or smaller than 3, plus or minus 3 on the x and y axis, and we want our Cooks to be less than 1. Okay, so first we get a lot of output. So we would scroll all the way down and look at your residual plots first. Now I see that I'm between -2 and +2 for the bulk of my data points, right? And so those behave pretty well. But then I've got this guy, I've got this guy, and I've got these weird things. And this is 4 on the x-axis to -2. And this is 7 something on the y-axis. So we're close, but we have some things that are of concern, but we'll just keep going. So we have a predicted probability plot. Before we talked about QQ, now we have the PP. So predicted probability, they kind of hug the line. We're going to say, you know what, that's normal enough. So the first bit of output that we get, you scroll back up and you get to your descriptive statistics, and you can see, means and standard deviations, nothing exciting. This is correlation, we've already gotten that. This is just output. And then we scroll down a little bit more and we get the model summary. This is the correlation coefficient we just saw here, right? It's no different, 0.726. Here we have 0.726. And then when we square it, we get our coefficient of determination. So we say 52.7% of BMI is explained by body fat. All right, and we have this adjusted R-square, which won't matter now, but we'll talk about it in a minute. So we would report it out. We'd say F1 of 250, so numerator, denominator, is equal to 278.9. P is less than 0.01. And then just FYI, because it's going to be in another document I give you, if you take the square root of f, you get a t statistic, and if you square the t statistic, you get an f statistic. All right, so then we go to coefficients, but before we do that, I'm going to scroll down to residual statistics, and I just want to check my standardized residual, and we are not between plus or minus 3. We are here, but we're not up here, right? So we kind of screwed up on the standardized residual, but that's all right. We just keep on trucking. And then here we do see that our Cook's distance, the minimum is 0 and the maximum is 0.5. So we are less than 1, so we're okay. We don't have any influential points. Now back to that y hat is equal to b naught plus b1x. This is what we'll use to build our regression equation to do predictions. This is our y-intercept, the beta naught, and then this is our slope, which is the beta 1. So what this means is that for if body fat were 0, your BMI would be 19, which kind of, sometimes it works and sometimes it doesn't work intuitively because nobody has 0% body fat, but that's how it would work. So for every unit increase in percent body fat, you would add 0.317 to this value to get the increase. So our research question was percent body fat doesn't predict the BMI, and our alternate was it does predict BMI. Our alpha is 0.05. Our test statistic we've just done. We're going to state our conclusion. Findings indicate that percent body fat is a significant predictor of BMI. Now look at, this is the omnibus test. Remember from ANOVA? This is the overall test that says, yes, the regression was significant because it's less than 0.05. And here's our coefficient of determination. So approximately 52.7% of the variance in BMI can be attributed to percent body fat. But we have to go back and look at this guy. So we're just going to say, we're going to report the t statistic, its significance, and the confidence interval for the predictor. So examining the predictor, we see that percent body fat is a significant predictor of BMI. T is equal to 16.7, p less than 0.01, and then our confidence intervals. It's a lot, I know. But you can just copy this and drop it into your homework and change the numbers and the variables. Okay, so now we're going to do the prediction equation. We're just plug and chug, right? So here's our intercept. I put it here. So y hat, just to remind you, is b naught plus b1x, right? Where b naught's the y-intercept, b1's the slope, y hat's the outcome variable, and x is the explanatory. So I plug it in. I have 19.3 plus 0.317 times x. So if I ask you, based on this regression equation, what would be a best prediction of BMI for a person with a percent body fat of 25? So all I do is I just plug in 25 for x. I do that, and I solve for BMI. I would go in, I would plug in my calculator. I'd say 25 times 0.317, get that, plus the 19.3, and I get 27.2. So that's the new BMI. And you will have to bust out the calculator to do these prediction equations because it doesn't come in output. All right. Now, if that weren't enough, we can add more than one independent variable to a regression equation. So a possible research question would then be, do percent body fat and age predict BMI? Now, the reason we would do this is because then we can control for one variable statistically as we evaluate the other. And all we do is we just add another slope. So we have beta naught, still the intercept, beta 1x, that's our percent body fat. And now we're going to do beta 2x, which is age. And here we have it. Beta 1, beta naught, beta 1 percent body fat plus beta 2 is age. And the outcome variable is BMI. I'm not going to take you through all the steps because you do the exact same thing you would do with a simple linear regression. But you can see here we're between negative 2 and 2. We had almost the same kind of outliers. Now we have a couple of other weird, we have this new one here because we've added another variable. So it's a little bit different, but very much similar to what we had before. PP plot looks the same. Now we're going to look at this adjusted R square. Everything else is the same, right? Our correlation coefficient's a little bit different. The more predictors we toss into our model, your R squared is going to go up. And since this is an effect size, it's misleading, right? So if I want to have, I have a strong effect, I'm just going to throw in all the variables I have. Well, you overfit your model when you do that. So we use this adjusted R square, which is this adjustment. It kind of pulls back a little bit. It's not much different than this R square, but we would use that one to state our coefficient of determination. So thus, 53.4% of the variation in BMI can be predicted by percent body fat and age. And here we have two variables in the equation. So we have degrees of freedom is 2 and 249, and our 144.7, or it could have been 0.8 if I had rounded, is P is less than 0.01, and our F observed is still the same. So I'm not even going to do the write-up in APA format because I'm not asking you guys to do that, but you would do it exactly the same way as you did the other one. But here you would report the T statistic for the percent body fat because it's significant, and for age because it's significant, and the confidence intervals. But we're not going to do that for now. I'm just going to show you. So say we had a 50-year-old with 25% body fat. What is this person's predicted BMI? Well, it's the same way as we did before. You would you have your what is it? The blanking y-intercept is 20.44, right? Plus 0.331, which is this slope here, times 25, which is the body fat. And then I'd say negative 0.031 times 50, which is the age, and we get the predicted body fat. All right. Now, logistic regression. What we were doing before is called ordinary least squares, and we're predicting the difference between that and what we're doing here is our outcome variable in multiple regression is continuous. Now, our dependent variable is dichotomous. So I can predict whether somebody lived or died. I can predict whether there's a presence or absence of disease. Anything where I have a dichotomous binary outcome variable with two levels, I can predict it. Pass, fail, right? Presence, absence, lived, died, whatever. I can do that now as my outcome variable. But we're using a completely different mathematical calculation. This is a natural log of the odds. Probability over 1 minus probability is the odds calculation. That's the equation for odds. When I take the natural log of it, it's called a logit. This side of the equation is familiar. We're doing the same thing. This left side of the equation is where it's different. Now the number E is a mathematical constant approximately equal to 2.71828, and it's the base of the natural log that is the unique number whose natural logarithm equals 1. Way more information than you need. All you need to know is that we're going to exponentiate the beta to take us out of logit and back to odds. Now the only thing you need to know is that you're going to see this in the output and that it'll give us odds, and I'll explain that. Now, I'm not going to have you guys do these calculations because I just can't do it justice in 1 week of lessons. But I wanted to show it to you so that you know in the future, if you ever do it for your master's thesis or a PhD, I want you to know that this is available and there are ample resources. I linked to a video, a YouTube video, and I also will show you a link in this PowerPoint for the written instructions. And if you want to do it with the project, we can meet outside of class time on Zoom and I can walk you through it. Okay, so dummy variables. I mentioned this before, and what that means is that it's basically like when we do value labels. You have a value of 0 and 1. You wouldn't do it 1 and 2. You'd always have it 0 and 1. And there are two different categories of the nominal, which is a qualitative variable. So for the dependent variable for this data set, I have heart disease present is equal to 1, and heart disease not present is equal to 0. And SPSS always assumes the higher value is the reference category, so presence of heart disease is the reference category, and I'll explain that in a second. So here's the link if you wanted to get this written out, step-by-step instructions. So what I want to know is, does weight predict heart disease, presence of heart disease? So analyze, regression, binary logistic. I go to analyze, regression. I come down, I leave linear, come down to binary logistic. I bring over presence of heart disease variable, and I bring over weight. I'm going to click save, and I'm going to ask for probabilities and group membership. Actually, I don't even think I talk about this in the PowerPoint, but this will give you, it adds columns in your data set, so you can actually go back and see the predicted probability for that particular individual. All right, so when you do this, you get two, your output's kind of weird. You get block 0 and block 1. And in block 0, this is the null model with just the intercept. It has no predictors in it. And in just using the intercept, we classify correctly 65% of the response variable. And then the rest of this we can just kind of ignore. Now we scroll down to block 1. Here we are at block 1, which is, it says method equals enter. Now we have our predictors in the data set. This is just telling us that they're there. This is Nagelkirky R squared. This is a pseudo R squared. Pseudo means kind of fake. Somebody has come up with a calculation to approximate a coefficient of determination. So this works just like it. I would say 11% of the variability in the DV is explained by the IV, but it's not everybody reports this, but this is the one we would go to. So here's our classification table. You can see the type 1 and type 2 errors where we've got 60 no, no, and 8 yes, yes, and we misclassified 27 and 5. And then we went from 65%, now we're only correct 68%. So that's not that great. All right, so the inference, right? We get the variables in the equation. Now we're not dealing with t-statistics, we're dealing with walled statistics. And it's different the way we infer this. Now we have the predictors on top, the constants down below, where the other, in multiple regression, they give us the constant up top. You just have to be careful. So we do know that weight is a significant predictor, because it's significant here, of presence of heart disease. So what we look to the EXPB, this is the exponentiated beta, and we're going to report these as odds in favor of the outcome. So here the outcome is the presence of heart disease. So the odds of getting heart disease is 1.04 times higher for each unit increase in weight. And that is how you do that. I know it's a lot of information. The only things we're going to deal with are correlation and simple linear regression.